Right, let's get started. So today we will finish the lecture 9. So orthogonal projections. So at the end of this lecture note 9, so we will see best approximation theorem, which is related to the closest point from the vector to the subspace W, as we discussed here. So we want to find out the closest point here. So let's go back. So we can prove y hat that we discussed so far. So orthogonal projection of the y onto the double subspace W is the closest point by this theorem, best approximation theorem. So let me start to let W be the subspace of Rn space and then vector y be any vector in Rn space. Then let y hat be the orthogonal projection of the y onto W. Orthogonal projection y onto W. Then y hat, orthogonal projection of the y onto W is the closest point. Closest point in W to y in the sense that the length of the y minus y hat is smaller than y minus vector v, arbitrary vector v, for whole vector v in W distinct from the y hat. It seems to very, very difficult, but it's very, very intuitive. This theorem say that, okay, so here is the subspace W, and let's suppose that here is the vector y, and let's suppose that here is the ortho operation of the y onto W, let's say y hat, then this y hat is the closest point from the y to W. This is the best approximation theorem. In other words, the vector y hat is called the best approximation to y by element of the W. Best approximation to y by the element of W, because in comparison to any vector, let's say v in W space, y hat is the closest point from the vector y to W subspace. In other words, the distance from the y to v, 그쵸? y to v, given length of the y minus v, can be regarded as error, I mean the distance or error using v in place of y, So in this case, if we use y hat to this vector v, then error will be minimized. So this theorem says that this error is minimized when v is equal to y hat. This is the best approximation theorem. So this is let me say this is the equation 3. This inequality leads to the new proof that y hat does not depend on the particular orthogonal basis used to compute it. So y hat does not depend on a particular orthogonal basis used to compute it. And it is different orthogonal basis for W were used to construct the orthogonal projection of the y. Then this projection would also be the closest point in W to y, let's say double star. This is the orthogonal best approximation theorem. So first of all, let's prove this one. So first of all, here is the subspace W, and here is the vector y, and here is the also projection of vector y onto W. So let's say this is a W hat, and let's take a vector v, arbitrary vector v in W distinct from the y hat. So what we want to do, we want to prove the distance of this one, length of the y minus y hat, is smaller than length of the y minus v, length of this one. As you can see here, as you can see this figure, you can easily say that this one, this line, is smaller than this line. 그렇죠? Much shorter than this one. But let's prove. So first of all, y hat minus v here. 그렇죠? y minus v in double space. 그렇죠? Because y hat and v are both in double space, right? So y hat minus v is also in double space. Then by the orthogonal decomposition theorem that we discussed last week, y minus y hat, it was the vector v, for example, 그렇죠? minus y hat is orthogonal to w, 그렇죠? orthogonal to w. In particular, y minus y hat orthogonal to the y hat minus v, 그렇죠? Because the y hat minus v is in double space, so they are orthogonal each other, right? And then, and then, let's consider this triangle. Let's redraw this triangle again. Here's y hat. Here is the vector v, 그쵸? The v. Then by the Pythagoras theorem, here, the length, the square of the length of the y minus v, this one is the sum of the square of the length of the y minus y hat, the square of the length of the y hat minus v, which was the Pythagoras theorem, 그쵸? Which was Pythagoras theorem. 그쵸? And intuitively, this one always larger than 0, 그쵸? Because we assume that v is not equal to y hat, so this one is always larger than 0. Then, so inequality follow immediately. So I mean this one, 그쵸? y minus v y minus y hat. So y hat is the best approximation for the y in double space. This is the best approximation theorem. Okay? That's it. And how to use this best approximation theorem? Let me show you an example. So distance from the point y or vector y in Rn space to the subspace w, which is defined distance from the vector y in Rn space to w subspace is defined as the distance from the vector y to the nearest point in w. 그렇죠? W is here, vector y is here, then distance determined by the nearest point, which was orthogonal operation y onto w. 그렇죠? Then find the distance from the y to w, which is spanned by u1 and u2, where the y looks like this, u1 looks like this, u2 looks like this. Looks like this. So the question is, what is the length of this vector when u1 and u2, arbitrary vector u1 and u2, basis for the subspace w. Let's prove this one. Let's solve this one. So, the first of all, by the best approximation theorem, the distance y to w is the length of the y minus y hat. 그렇죠? So we already know what is y. So the question is, what is the y hat in this case? Y hat is also operation of y onto w. So question is, what is y hat? This is the problem. Okay. So let's prove this one. Because we already know why u1 and u2 is an orthogonal basis for the w, because this one they are spanned by w was spanned by the u1 and u2, and they are orthogonal each other. So u1 and u2 are orthogonal basis for the w space. Then y hat, it's going to be, it was defined last week, 그쵸? It's going to be y u1 over u1 inner product u1 times u1 plus y hat y plus u2 y inner product u2 inner product u2. So we already know what is y and what is u1. Then you can easily compute this one. This very, very simple inner product computation. How? So y was the -1, -5, 10, and u1 was -5, -2, 1. Then it's going to be what? 15. Then this one, -5, -2, 1 times -5, -2, 1. Then it's going to be 30. So 15 over 13 times u1. Similarly, you can compute the -21 over 6 times u2. Then, because you already know u1 and u2, it's going to be looks like this. And finally, this one can be summarized to the -1, -8, 4. You can easily compute this one. So finally, you got a y hat, which is equals to -1, -8, 4. Then y minus y hat. Y was here, y hat was here, and y minus y hat is going to be 0, 3, 6. 0, 3, 6. Then the length, square of the length of this one, it's going to be the square of the 0 plus square of the 3, square of the 6, from each element, then which is going to be the 45. Then the distance from the y to y hat, y to w, y minus y hat, it's going to be square of the 45, it's going to be the 3 square root of 5. So in other words, the distance from the y to the nearest point in w, it's going to be 3 square root of 5. This is one of the way to use your orthogonal basis of frequency theorem to understand the distance between vector and substrate w. Okay. Finally, there's one more theorem, but it's exactly same to the previous theorem, orthogonal projection theorem. But in this case, we just assume that our U is also normal basis for the substrate W in our space. Then projection of the Y onto W, which is going to be, for example, in previous theorem, it was something like this, and something like this, or something like this. But in this case, if we consider also normal, then U, inner of the U, length of the U should be 1. So in this case, it should be 1, right? So in other words, in case of the also normal basis for the subspace W, projection of the Y onto the W subspace is going to the Y inner product U1 times U1, Y inner product U2 times U1, U2, Y inner product UP times UP. if we view matrix U, which is consisting of the y u1, u2, and up as a column vector, then this one can be shortly written as u transpose y. U transpose y for all y in Rn space. For y in Rn space. That's the theorem 10. In other words, this is very, very simple. You can just make this matrix multiplication form from this one. This is the theorem 10. Let's prove. It's very, very simple. First of all, let's say this is formula 4 and this is formula 5. The formula 5 or equation 5 followed immediately from the 2 in the arithmetic component theorem. 그렇죠? 설명했죠, 요거. 그렇죠? And also equation 4 shows that fraction of the y onto w is linear combination of the columns of the u using the weight. This one, and this one. Linear combination of u1, u2, and up by using this one and this one as a weight. 그쵸? 쉽죠? Then the weight can be written as, we can rewrite this one in a transpose form, showing that they are entries in uty, because ut ut can be written as u1 transpose, u2 transpose, and up transpose and y, vector y. 그쵸? Then this one is going to be u1 transpose y, u2 transpose y, up transpose y. 그쵸? 그쵸? Then this is the coefficient. It was coefficient. Then you can rewrite this one is because it was a linear combination of the columns of u using the weight of this one. So it's going to be y u. Let's rewrite again. u1 which was u. Okay, let's continue. So u1, u2, up times this one. 그렇죠? 다시 씁시다. This one. So u1 transpose y, up transpose y. Then it's going to be u transpose vector y. That's it. So we can simply represent fraction of y onto w as a u transpose y for all y in our space. This is the theorem 10. Okay, so in the next lecture note, we will use this theorem, this kind of theorem, to derive the algorithm to better factorize your matrix A. Okay, that's it. So this is end of lecture note 9. If you have any question, please send me an email. Then today, let's move to the lecture 11, Gram-Schmidt process. Gram-Schmidt process, where we can derive the QR factorization, which is another factorization comparing to the LU factorization. This QR factorization is the generalized algorithm to factorize your matrix better. Okay, so before that, let's discuss the Gram-Schmidt process first. Okay, so this is chapter 6.4, Gram-Schmidt process. So, first of all, before starting, let's review. Where is that? Yeah, let's review the concept of orthogonal projection and complement. Orthogonal projection and orthogonal complement. 그렇죠? So, if vector y is here, y hat was orthogonal projection, and vector z was orthogonal complement. 그렇죠? The y hat is called the orthogonal projection of the y onto w. Vector z is called the orthogonal complement or the complement or component of the y orthogonal to w. Component y orthogonal to w. It was a definition which can be drawn here. 그렇죠? y w is here, vector y is here, y hat. 그렇죠? And vector z is the y minus y hat. Then we discuss how to compute this one by using the basis for the w or the orthogonal basis for the w or also normal basis for the w. Then we can directly compute this one, right? Then in this chapter, we will use the technique we derived, the formula that we derived so far, and we will propose the Gram-Schmidt process. Right, here. The Gram-Schmidt process. Gram-Schmidt process. The Gram-Schmidt process is a simple algorithm for producing orthogonal or orthonormal basis for any non-zero subspace or Born space. Right. So in other words, last chapter here, we just assume that if we know orthogonal basis or the orthogonal basis for the subspace W, then you can represent any vector y, any projection of the y onto W space by using this formula, right? Then the question is how to find the orthogonal basis for the arbitrary subspace W or orthogonal basis for the arbitrary subspace W. That's the topic of the Gram-Schmidt process. The Gram-Schmidt process is a simple algorithm for producing or the finding orthogonal and orthonormal basis for the any non-zero subspace in Rn space. This is the Gram-Schmidt process. Then you can find out any kinds of orthogonal the orthogonal projection of the vector y onto arbitrary subspace W. Then which can be used in the QR factorization later, but this is just a Gram-Schmidt process. So let me show you example first. Let's suppose that space W. So space W is spanned by x1 and x2, where x1 is 3, 6, 0, and x2 is 1, 2, 2. First of all, construct an orthogonal basis V1 and V2 for the subspace W. So, first of all, x1 and x2 was basis for W because the W was spanned by x1 and x2, right? But they are not orthogonal basis. Why? x1 in product to x2 was not 0, right? So, orthogonal basis means it should be basis for the space W as well as the length, the inner product of the vector V1 and V2 between them should be 0. Then it's going to be orthogonal basis. Then if we can find out this one, we can find out the orthogonal projection of the arbitrary vector y outside the W by using the formula. Looks like this. 그렇죠? That's the topic of the Gram-Schmidt process. So, in other words, question is construct orthogonal basis of V1 and V2 for the W space. Right, let's do that. Our strategy looks like this. Let's suppose that, okay, so these vectors defined in a R3 space, let's suppose that x is here, x2 is here in our C space. Then we want to find out V1 and V2, they are orthogonal each other. So in Gram-Schmidt's process, first of all, we just assume that V1, first V1 is the x1 itself. V1 is x1 itself. Then we want to find out V1, V2, which should be complement of the x2 orthogonal to x1. In other words, we want to find out V1 defined looks like this. Orthogonal to x, or the orthogonal to line spanned by x1 or V1. So, question is, so how can I find this one? We have to find out orthogonal projection of x2 on line spanned by x1 or v1. Then you can just find out vector v2 by x2 minus x2 looks like this. That's the that our strategy. Then v1, v2 can be the orthogonal basis for the w because they orthogonal each other and they are basis for the substrate w. Okay, so how can I find this one? We can rewrite v2 as x2 minus this one. We already know how to compute the fraction of the x2 on arbitrary substrate w, arbitrary substrate w, so which is going to be x2 time, x2 inner product x1 and x1 inner product x1 times x1. Alright. So we already know x1 and x2. Then you can simply compute this this equation 1 to 2 minus 15 over 14 5 times 3 6 0, which is going to be 002. So in this case, V2 and V1 and V2 are orthogonal each other, and V1 and V2 is the V1 and V2 can be represented by the x1 and x2, 그렇죠? x1 and x2. In terms of the x1 and x2, then they are basis for the w, and then V1 and V2 is orthogonal basis for the substrate w. So yeah, that's it. So that's the way to find the orthogonal basis for the substrate w. I'd like to show you one more example. What time? 14. Alright, today I will finish here because we already discussed so many things. So yeah, so next week we will derive the Gram-Schmidt process in a generic form here. Then we will introduce the orthonormal basis and the QR factorization. Okay, that's it. So thank you very much. And if you have any question on today's lecture, please let me know or come by my office, Science Library Building, 404C. Okay, thank you very much and see you next week. 여러분 오늘 강의는 이 정도 할게요. 그래서 오늘 여기까지 하면 될 것 같고요. 고생했고요. 우리 다음 주에 보도록 합시다. 고생하셨습니다.